Hi, welcome back to Mechanical PE Exam Prep. This is Dan. Today we're going to be working on a thermodynamics problem. This is a good problem for working with turbines, talking about how to draw thermodynamic cycles, talking about when you can and can't use the tables for a lookup versus when you should use thermodynamic properties. We're going to spend a lot of time in this problem talking about assumptions and which assumptions are valid and when you should make certain assumptions. So even though there's one particular path that we'll take to solve this problem, we'll talk about various other paths that would be applicable in similar problems and why we're not using them here. And that's really the bigger picture as you work through a number of examples is how do you categorize a problem, how do you break it down and solve it in a way that works for what's been given in that particular situation. So hopefully all the examples we do sort of focus on that kind of learning. This one will be no different. Let's get started. So we have a low humidity clean room receives some of its mechanical energy from a gas turbine. Gas flowing through the turbine is a mixture of carbon dioxide and nitrogen. The following data is available. We have the turbine mechanical efficiency, the turbine isentropic efficiency, the turbine power output, the gas mixture flow rate, the turbine inlet gas temperature, and exit gas pressure. And then we have the gas properties, specific gas constant, specific heat at constant pressure, and ratio of specific heats. And they want to know what is the turbine inlet pressure, what's the efficiency of the power generation process, what's the entropy change of the gas mixture, and they want us to sketch and label the TS diagram for the expansion process. So quite a few things to figure out there. I don't think this would be a problem that you would see. Maybe one of these questions would be a typical problem on the test. So this is a considerably longer and more in-depth problem than you would see on the exam. So first, let's draw a little diagram of the expansion process. Essentially, we have a turbine. So what does a turbine really do? You have some mass flow rate in of high pressure gas, and then that gas goes through an expansion process and it comes out at a lower pressure and temperature. And the result of having gone through that process is that it's done some work. So some work comes out of this thing. I like to think of a turbine as the exact opposite of a pump. A pump, you put power in, right? You're turning a shaft, and the result is that a fluid of some kind comes out at a higher pressure. Turbine's the opposite. You come in at high pressure and leave at low pressure, and you do some work. So a pump, you put energy in, and a turbine, you get energy out. So let's assign variables to some of the things that we've been given. We have the turbine mechanical efficiency, so we'll call that subscript M. And then the isentropic efficiency would be eta sub S. And then we have the turbine power output. I'll call that W dot out. And now just note that's the actual power output. Then we have the flow rate of the gas mixture, which is M dot. And then we have the inlet gas temperature. So that's the inlet of the turbine. I'm calling that state 1. So I'm going to call that T1. And then we have the turbine exit gas pressure. That's state 2. So that's P2. And then we have the gas mixture properties, the specific gas constant, which would be R. And then we have the specific heat at constant pressure, which would be C sub P, and the ratio of specific heats, which is K. Just a word on R, they've given it to us in BTU per pound degree Rankine, and that's fine. But if you just want to, I'm skipping ahead a little bit, but take a look at page 2316, table 23.7 that we're going to use. All of the R values there are given in foot-pounds per pound mass degree Rankine. So if you want to convert, and you may or may not need to, but I just wanted to point this out, you can just use the fact that 1 BTU is equal to 778.17 foot-pounds force. So you can multiply this number here by 778 foot-pounds, and BTUs goes away, and we end up with 44.36 foot-pounds per pound mass degree Rankine. Okay, so this is all the information we have. The first thing they want us to find out is the turbine inlet pressure. I'm actually going to skip to part D and do the sketch first because I think the sketch helps understand what's going on. We may not have all the information right away, but we'll fill it in as we go along, and by the time we get to D, we should have it done. So they want a TS diagram. T being temperature, S being entropy. And on TS, the pressure curves, or the lines of constant pressure, look kind of like this. So we'll call this P1 and P2. And we know P2 is 16 psia, and we don't know P1. That's one of the first things we want to find. So imagine this state M1 is known. We can also say we know the temperature, T1. T1 equals 240 degrees Fahrenheit. So as this expansion happens, if it were perfect isentropic efficiency, then state 2 would be directly below. Remember, isentropic means no change in entropy, so no losses. So if it's on TS, that has to be a perfectly vertical line from state 1 to state 2. Since we know it's not, the path it actually takes is probably more like this. And we'll call this state, to where it actually goes, 2 prime. Notice 2 and 2 prime have the same pressure, regardless of whether it expands isentropically and goes straight down, or if it has some inefficiency and takes a little bit of a curve, it's going to reach the same final pressure at state 2. But the difference is, if it were to go to 2 and be 100% efficient, it would go to a lower temperature. So you'd have a bigger delta T during that expansion. It doesn't. It only goes to 2 prime. So that's T2 prime. And if we're interested in it, we could probably also find T2. We'll see where the problem takes us. But I just wanted to kind of sketch it out, frame what we know. And we've marked the temperature at state 1. We've marked the pressure at state 2. And I think that's pretty much all we know right now. So as we go through the problem, we'll hope to find P1 and T2 prime. So for part A, what is the turbine inlet pressure? We can start by making a decision as to one of 2 paths we can take. One path would be to try to use lookup tables. However, this isn't a steam turbine, so we can't just go to the back of the book and, based on some properties we know, look up the different enthalpy values for steam. Instead, we have this mixture, and our mixture is some nitrogen and some CO2. And what we have are the gas properties for that mixture. So a better way to go about this, instead of we never even have to figure out the proportion of nitrogen and carbon dioxide we have. We can just take the R, the CP, and the K values and use the thermodynamics equations on page 24.8 and 24.9. There's a whole bunch of thermodynamic properties. It's almost overwhelming. It's like 2.5 pages of properties. And the hardest part about using these is simply figuring out which one you want to use based on the variables you have and the variables you want. In our case, we want P1 for an expansion process, and we can list some of the assumptions for that process. We know it's not isentropic, but we might be able to account for the fact that it isn't. It's not isentropic, but we might be able to account for the fact that it isn't. So I'm going to put that one there. Adiabatic, meaning there's not a significant amount of heat transfer happening during the expansion. That's not to say the temperature isn't changing, but the Q, the amount of heat going in and out of the system, is approximately 0. Steady flow, we can definitely make that assumption because we know that there's some flow rate, m dot, gas mixture flow rate, which isn't changing. And we can also make the assumption that there are these gas mixture properties and that these properties are constant. That is to say that it's an ideal gas. So with these assumptions, my eyes are drawn to the bottom right corner of page 24.9, the isentropic steady flow systems. If we can only deal with this assumption here, if we can make it isentropic, then there's a very nice formula, 24.139, and I'll jot that down, 24.139. This one says that the change in enthalpy equals Cp T1 times 1 minus the ratio of P2 to P1 raised to the K minus 1 over K. So that's a bit of a leap. Now all of a sudden I've kind of pulled out this equation, and I know that's it's hard to go all the way from how do we solve this problem to here's the equation you need to use. I guess part of what I can't really replicate in a video is the experience of doing lots of problems to figure out what equation you should use. But the only process I went through to select this one was what we have and what we want. I made these assumptions, so that's what got me to the bottom right corner of 24.9. And then I looked at what we have. We have P2, we have K, we have CP, and we have T1. We don't have P1, that's what we want. And the thing that we would need going in is delta H, which is the change in enthalpy for this expansion. It's the amount of energy that comes out of the system as it expands. And it has to be with the assumption that the process is isentropic, which I'm going to show you how we can account for that. And almost all of these equations pivot around the idea of, I shouldn't say all of them. There's a bunch that will help you specify P1, a pressure, a temperature, a specific volume, something like that. But a good number of them, maybe half, pivot around the delta H or the work done or the change in internal energy. So I kind of already had an inkling that this was going to be involved. Okay, so our new mission en route to getting P1 is to calculate the change in enthalpy that comes out of this cycle, assuming it's isentropic. And we're going to start from the work. So the power, we know the power output for this cycle. We know it's 5.2 bhp. So we have W dot out equals 5.2 bhp. But we also know that the process is not isentropic. If it were isentropic, then it would produce more power. How much more power? Well, we can say that the work out for an ideal or isentropic cycle would be the 5.2 horsepower divided by that efficiency, which is 5.2 over 0.7, which is 7.429 horsepower. So that's the power that the cycle would produce if it wasn't losing 30% on the fact that it's not going straight down, it's taking this curve. Then the other thing that's hurting us is the mechanical efficiency. The mechanical efficiency is 85%, and the way that the cycle compensates for that is it just pushes a higher flow rate around the loop than it really needs to. So we know the actual flow rate is 340 pounds per hour, but we also know that that includes additional flow to make up for this imperfect mechanical efficiency. So a way of writing that out would be to say that the actual flow rate is the ideal flow rate, which would be the least possible flow to produce the desired effect, over the mechanical efficiency. So we're dividing by a number less than 1. The result is going to be larger than the ideal flow rate. And we have to rearrange that because we know the actual flow rate and the efficiency. What we're finding is the ideal flow rate. So m dot ideal equals m dot actual times the mechanical efficiency, which is 340 pounds per hour times 0.85. And that equals 289 pounds per hour. Okay, so let's review what we just found. We found the power that the cycle would actually put out if it was isentropic, and the flow rate that would actually be required if the mechanical efficiency were 100% instead of 85%. Hopefully that makes sense intuitively, that you're getting more power with a lower flow rate, with less flow rate, if the mechanical efficiency is 100%. So now what we can do is find the change in enthalpy for this ideal cycle. We know that the power out ideal is equal to m dot delta H. I think that's a formula somewhere, but it's the kind of formula that I wouldn't expect you to look up. This is one that you should just know, and you will from you do enough of these examples. Another way is to think about this is like Q equals mCp delta T. Delta H includes Cp delta T. It's all baked in because it's already per unit mass. Okay, so it's delta H we're looking for. We know the mass flow rate and we know the ideal power out. So the change in enthalpy then is W out over m dot which is 7.429 horsepower, divided by the 289 pound mass per hour. And then we need to get rid of horsepower. So we're going to do 1 horsepower is equal to 550 foot-pounds per second. But we don't really want seconds, we want hours. So we'll say 3,600 seconds per hour. That gets rid of seconds, and that gets rid of horsepower. Also, the 1 over hours goes away. So now all we have is foot-pounds force per pound mass. Ultimately, what we want is BTU per pound. So we got to get rid of foot-pounds. We're going to divide by 778 foot-pounds per BTU, foot-pound force per BTU. And we'll end up with BTU per pound. So when you do all that math in your calculator, you will get 65.42 BTU per pound. And I just want to point out, to tie this back to the original diagram, this is the difference between state 1 and state 2, not 2 prime, because we made the assumption that it is isentropic, so it expands all the way down, straight vertical line, constant S. So this would be delta H isentropic, or you could say H1 minus H2 equals 65.42. Okay, so now we know delta H. We can actually go back up here and plug that in, and I'm going to need a little space to work out the algebra, so I'm actually going to start from down here. We have 65.42 BTU per pound equals CP, which is 0.218 BTU per pound Rankine, times T1. Now T1 has to be in degrees Rankine. So originally it was given to us as 240. You have to add 460 to that. So that's 700 degrees Rankine. And then we have 1 minus the ratio of the pressures, P2 over P1. P2 is known to be 16 psia, and P1 is unknown. That's what we're after. And that's being raised to K minus 1 over K, where K is 1.355 minus 1 over 1.355. That's an exponent, by the way, not multiplication, just to be clear. Now we can multiply these two, 0.218 and 700, and then do 65.42 divided by that result. We'll do all that in one shot on the calculator. I get 0.4287, and being a little sloppy with units here, but the Rankine goes away, and then the BTU per pound divides away with that. So we actually end up unitless at this point in time. And on the right side, we have 1 minus 16 psia over P1, and we have that's raised to 0.262. I've simplified this. Now we could subtract this on the right and add that over. So we end up with 0.5713 equals 16 over P1 to the 0.262. And now we have to raise both sides to 1 over 0.262 to get 16 over P1 by itself. 0.5713 to the 1 over 0.262. That equals 0.118. And finally, we can get P1 by itself is 16 over 0.118. P1 is 135.6 psia. Now let's sense check that answer. Is that a reasonable pressure at the inlet of the turbine? What was it? 135.6. Well, it's considerably higher than P2, so it makes sense if it went through an expansion process that P1 would be 135.6, so I'll buy it. And that takes care of this guy. Next, we're going to find the efficiency of the power generation process. This one is actually surprisingly easy for how much was involved in part A. The overall efficiency has to take into account the fact that it doesn't have perfect mechanical efficiency and it's not isentropic. So we really just need to multiply the two efficiencies together, and that's going to do it for us. So that's 0.7 for the isentropic and 0.85 for the mechanical. So we get 0.595 or 59.5%. That takes care of B. And now what's the entropy change of the gas mixture? So there's another equation, and it's nearby the other ones that we were using for this problem. It is on page 24.7, specifically equations 2450 and 2452. We're still assuming that this is an ideal gas with specific heats. However, we're no longer assuming that it's isentropic. So this is the point in the problem where we drop that assumption and say, no, it's not isentropic. I now want to deal with the fact that it doesn't come straight down from 1 to 2. It instead goes on a curved line from 1 to 2 prime, and I want to address that in part C. So looking at these two equations, we have delta H equals Cp delta T. And in this equation, we don't know delta T because we don't know T2. We only know the inlet temperature, but we don't know the outlet temperature. And really, we don't know delta H because we know delta H assuming it's isentropic, which is H1 minus H2. But we don't know H1 minus H2 prime. So we can relate those by using the isentropic efficiency, which is to say 0.7 is equal to H1 minus H2 prime over H1 minus H2. Or another way to say the same thing would be delta H actual over delta H ideal. And we know delta H ideal, we found that earlier, it was 65.42 BTU per pound. So we could find delta H actual, which is 45.8 BTU per pound. That allows us to substitute back up into this equation. So we can say 45.8 BTU per pound is equal to Cp, which we know. Cp is 0.218 BTU per pound Rankine times delta T. Delta T is really T1 minus T2, right? Because it's cooling. And T1, we know, is 240 degrees Fahrenheit minus T2. And I'm being a little loose here because I'm mixing Fahrenheit and Rankine, but that's because we're doing a delta T. So the difference between Fahrenheit degrees is the same as Rankine because they're the same size degrees. They're just offset by 460. So I'm going to divide by 0.218 on both sides, and we find out that delta T equals 210. So 210 degrees equals 240 degrees minus T2. So T2 must be 30 degrees. So let's actually go back up and label the diagram with that. And now we have, I think we just finished part D, because we have T2 prime equals 30 degrees F. And is that reasonable? It started out at 240 and it expanded, so its pressure went down and its temperature went down. I think that's reasonable. And now that we know the temperature at state 2, we can invoke the next equation, which is 2452. And there's two versions of this. There's one that calls for Cp, constant pressure, versus Cv, constant volume. We're going to use constant pressure because that's what we've been given here. And that equation is delta S, the change in entropy, that's what we're after, is Cp ln T2 over T1 minus R ln P2 over P1. And we know Cp, we now know both of the temperatures, we know both the pressures, we know the value for R. We're pretty much fully defined. We can plug and chug, and we should be able to get delta S. So I'll go ahead and populate these values. Cp is 0.218 BTU per pound Rankine. Temperature ratios always have to be in Rankine. That's important. So T2 is 30, but that's really 490 degrees Rankine over 700 minus R, which is 0.057 BTU per pound mass Rankine times ln P2 over P1, which is 16 psia over 135.6 psia. And I do it one term at a time and then add them together just to make sure I don't make any mistakes. The first term actually turns out to be negative 0.0778 BTU per pound mass Rankine. And the second term turns out to be negative, but then it has a minus sign, so it ends up positive 0.122 BTU per pound mass Rankine. And I think that's interesting because what that's basically saying is that the temperature change is a negative effect on the change in entropy, but the pressure change is a positive effect, and the net result is positive, which we would expect because things always tend toward positive entropy, we get delta S equals 0.044 BTU per pound mass Rankine. That is the answer to part C, entropy change of the gas mixture. And as I said before, for part D, we've basically labeled the whole TS diagram now. We know we fully defined state 1. We didn't fully define state 2. We never found the temperature, but we know it's the same pressure, and we're not actually interested in the temperature because in reality it's not isentropic, so we're more interested in 2' than in 2. So I will call part D complete as well. And I think if you take away one thing from this problem, it should be the idea that you can break these sorts of problems into 2 major classes. The ones where you do a lookup, usually it's a steam turbine, and you're going into the steam tables, looking up enthalpies at different states, maybe even working your way around the whole cycle, versus problems where you don't know it's steam, it's some other mixture, and you have to use the thermodynamic properties and the specific gas constant, the specific heat, and the ratio of specific heats. So you're doing more of a brute force thermodynamics approach, which this certainly was. Any comments or questions, please leave me a comment. If not, I'll see you in the next video.